Okay, let's go ahead. It's a couple minutes after, so let's get started. I've seen a few questions, so keep putting, as usual, over there in the chat anything you'd like me to work. This beginning part will be review, and then we'll go to chapter 3. That's what we're going to cover today. And we'll try to do as much, get you guys going with your homework as we can during this time. So before we go over anything from chapter 2 or even 1, any review stuff, are there any logistics questions, like, when something's due, or grading, or anything like that? So if you got a question, you can either unmute yourself or put it in the chat. So let's cover logistics questions now, and then we'll get to content and review in a moment. Great question, Brian. Thank you for bringing that up. A few folks have emailed me. So Brian's asking about late homework for partial credit. And in general, I've set up whenever we have, or this was my intention. So whenever we have an assignment in a Dropbox, I didn't put an end date on purpose. I put a start date and a due date. So that means you could submit, I think they're supposed to always be closing at 11:59 p.m. on Sundays or Wednesdays. And so suppose it's Monday morning and you're getting yours in, things happen, you had to travel or something, you can submit it, no problem. And it'll just show us like how many hours or how many days it's late, and you will get credit. You won't get full credit, but the later it is, then it sort of keeps knocking it down. And so we understand, especially this semester during COVID, that things like this happen, and that's why I purposely set them. So, and in general, Chloe and I are focusing on mastery and understanding. And so if you didn't get something in, don't just leave it as a 0. Please submit something eventually. And that exercise of submitting it not only gets you some credit, because we don't want to have 0 sitting there, we want everyone to do well, but it also helps you prepare for the final, right? So don't just like blow a week off and not submit things. Get them in when you can. Thank you, Brian. Good question. Okay, so other logistics questions? Okay, well, if you think of something else, please, again, put it in the chat. But for now, we're going to jump to the review. We'll use this time to go over anything, module 0, 1, or 2 that you want to look at. And once we're done that, we'll move to chapter 3, which fortunately is kind of a shorter chapter this week. We had a lot to cover in chapter 2. Okay, so in chapter 2, I've seen a few emails, and oh, this is logistics. So office hours, we had an office hour on Monday. So as needed, if I start getting a lot of questions from folks and I see that they're the same types of questions, I'll do an office hour. And so we had on Monday an office hour from 4 to 5, and Will and Addie and Samantha and Avery and who was it? Something with the C, Cooper, Carson, or so about 5 or 6 folks were there, and you can drop in for as little as much as you want when we have those office hours. And so they asked some really good questions, and those are good questions for the entire class to see. So we recorded the office hours, and then I put them in Oaks. So anytime something is done with this class that could be advantageous to the entire class, I will make sure I put that in Oaks. So if you go back and look in module 2 of Oaks, one of the videos under the course material will say, recording of a virtual office hour on such and such date, just as these classes. So a couple people have emailed me that they had to go home for different emergencies, even today. So this class is recorded. It takes several hours. Usually it's not till I don't get an email from Zoom until 9 or 10 o'clock at night, and then I have to process that in YouTube. So always by, usually by midnight before I go to bed, have that. Today's class will be in Oaks under the module that we're working on. So you can always see those. Okay, so then again, so all that was a preface to say that the folks asked some great questions on E's and LNs. So we got to practice a lot of E and LN on Monday's office hour. So we'll do a little bit today, as much as we have time. But if you still need more review on how to take the derivative of an E, how to take the derivative of an LN, how to solve E equations, how to solve LN equations, go back. There's a whole hour of extra material where we worked examples. Okay, and then I see a good question here from Lauren. Thank you. So your challenge problem, I believe I set the due date. I gave you a little more time. I think I gave you till Sunday for this first challenge problem that you're working with your team. And so you have to get up with your team members. You could do that multiple ways. Some of you asynchronous, some of you synchronous. You can meet on campus if you're all there. However your group meets, you want to probably take multiple times to meet to attack that challenge problem. So first of all, you have to choose which challenge problem does your group want to tackle. I think there were 3 or 4 choices for this first one. And then once you've decided that, you start opening your team's Google Doc, which is also in that assignment. We went through that, where to find it in Oaks. Ask your teammates if you're still not sure, but there will be an assignment for the challenge problem. And in that, you find your group's number. So if you're group 7, you click on that link, it opens up a Google Doc, your team starts working, and you can all type in there together at the same time, synchronously, asynchronously, and working out which problem you want to work on. There's a couple introductory questions at the top of that that'll say, you know, which pages do you think your team members maybe need to review to understand this concept? What do you think is going to be tough about this problem? So you're going to answer those that are just sort of prompting you to think, you know, intentionally and deliberately about that particular challenge problem. And then you have to write, once you've done, you know, worked on it together, then you write a final report together, and you have to write what your contributions were to that project as a team member. So just follow the Google Doc, it guides you through. And then your final report is what we are, it's a big part of your grade. So part of the grade is the contribution sections and the sort of pre-work and scratch work up here, contributions, and then your final report. And in that final report, you're solving that problem and answering it. And that is due Sunday. So again, go in there and check in module 2, the challenge problem. It's your first challenge problem. Okay, I hope that answered it, Lauren. If you still have something specific, put it down there in the chat. Okay, so I see a few questions here again on E's and LNs. So we're going to review some things from chapter 2. And I think one I'd like to look at that actually hits on several concepts is this following problem. Okay. Okay, thanks, Addie. So also one other comment too, I remember this question. I think it was Cooper asked this. So remind me if you can't see during this live lecture, I can write a little bit bigger, make my font a little bit bigger. But on the recorded ones, several of those have already been recorded, but in the future ones, I'm going to try to write a little bit bigger. But a couple things you can do on those recorded ones is they're in YouTube, so you're going to be clicking on a YouTube link to open them. And when you do that, you can obviously go full screen, so maximize whatever your machine is that you're looking at. And then there's also over in the right corner of YouTube, there's a little gear button for the settings, and you can adjust the settings to the quality to make it increase it to the maximum quality that your internet can provide you, or Wi-Fi service that you're on. Make that the maximum that you can, and you should see that it'll make this much clearer, the font there. So a little trick if you're at home and having a little trouble with this, but I'll do what I can on my end now that for any of the ones that haven't been recorded yet. Okay, so this problem, we want to find the CPs for this function, and then we want to answer a couple other questions after that. What is the derivative at x equals 1? That's x equals 1 is then a point of tangency for us, a point that we're interested in. And we want to know, is the function increasing there? So a couple of these questions we can kind of get a feel for if we took out a tech tool and visualize this. But we don't have to do that to answer this question. So let's just try this straightforward with the calculus, and then we'll come back and see if the tech tool verifies what our calculus does. Okay, so the CPs, the definition of a CP, it's a critical point. What makes it so critical? It's the place where you have a horizontal tangent line. To have a horizontal line, you must have a slope of 0. So the definition of the derivative is the slope of the tangent line. So I'm going to take the derivative of this function and set it to 0. And that, by solving the equation that results from that, I am getting a critical point. Now, the reason I put this problem in here is it has some e's, some polynomials, some indifference, but it also has, Addie's question was about the product rule. This also uses the product rule. So we get to practice a lot of our differentiation rules with this one example. Okay, so the definition, or the form for the product rule is you have to notice you have two things being multiplied together, which we do. And then the rule is, it's the first times the derivative of the second. We'll need a little more space here. Plus the second times derivative of the first. And that's, again, just the structure. It's just a rule that keeps us from having to use the limit definition of the derivative. Okay, so that means here's our first function, here's our second function. There's some boxes out of these 4 boxes that we need to fill in. 2 of them are just copying. So like the first function is e to the x, that goes right there. The second function is this polynomial, x squared minus x minus 5. That goes in the back. And then the 2 remaining boxes, we need to take derivatives. The first one here, 2 prime, the derivative of the second function. Well, this is the easy one because it's a polynomial. No problem, right? 2x minus 1 plus 0 or minus 0. So just 2x minus 1. And then in the back, we need to take the derivative of the first function. The first function is e to the x. The derivative of e to the x is e to the x. It's the simplest e to the power function. Okay, now we have to solve this. So this big equation here, that's really messy. So it's going to take us some reviewing some algebra, simplifying terms, distributing, and then we'll be able to solve it. One thing I do see though is like there's a bunch of stuff in front of a plus sign and a bunch of stuff after a plus sign. So I'm sorry, go ahead.
Which problem are we on?
We're just working one that was in the back. This is 5L on page 199.
Okay.
And then I added some stuff to it. So the problem originally was just find the CPs, and I added a little bit more about what is the derivative at 1. Okay, so to get the CPs, again, we have this structure of some stuff in front of a plus sign, some stuff after a plus sign. So I'm hoping, though, maybe I can factor some stuff. There's a lot of ways to do this next step. I'm just going to show you one that I think is maybe easiest. I see that this has some e to the x and this has some e to the x. So I'm actually going to factor that out. And what I'm left with in the first term is 2x minus 1. What I'm left with in the second term is x squared minus x minus 5. So I factored what was common to each term, which was an e to the x. I pulled it out. To check that I've done that correctly, I can do the multiplication in the forward direction. Yeah, I do get that term. E to the x times this polynomial. Yeah, I get the second term. Okay, the point of doing that was what I'm left with in these brackets. I can simplify. So I have an x squared, and then I have a plus x and a minus 6. It looks like, have we made much progress? We've made a little bit, because I can now do one more factor. I can take that quadratic term, x squared plus x minus 6, and see if I can factor that. X squared only factors into x and x. 6 factors into 3 and 2. And I need that to be plus minus like that. Now I have 3 factors multiplied together and equal 0. The only way 3 things can multiply to 0 is if at least one of them is 0. So I can set each factor to 0. So I can say e to the x equals 0, and x minus 2 equals 0, and x plus 3 equals 0. Now I need to solve each one of these. The second two are easy. We get x equals 2 as a CP, x equals minus 3 as a CP. And the first one, again, back from your videos from module 2, e to the anything equals 0 has no solution. So there's no value of x that can ever make e to the x equals 0. If you tried undoing the e with an ln, its inverse operation, you'd see that there's no solution as well. So we have finished the first part. We found the 2 CPs. So we found that there was a CP at x equals 2 and at x equals minus 3. But there were a couple more questions that were asked, which is, what is the derivative at 1? And we've taken the derivative. It's just a matter of plugging in. In fact, I'll make some space down here. Every one of these is the derivative. So I need to find f prime of 1. That's e to the 1 times 1 plus 1 minus 6, which is e to the 1 times minus 4, which is minus e to the 1, which is like, e is about 2.718 or something. So this is definitely negative. This is less than 0. So we've answered the next question. The derivative at 1 is negative, not quite 12, so maybe somewhere around 10, or between 10 and 12, whatever that decimal turns out to be. And then, is the function increasing there? Because this is a negative sign, it's less than 0, that means the function is actually decreasing there. So we'd say a big no here, it's decreasing. And the slope is negative 4 times e. So we did a lot of calculus though. Let's see, like, what's the point? What is the visual that goes with that? So let's graph this function. So I'm going to share the screen and see if our calculus checks. Go to Desmos. Enter the original function. So y was e raised to the x times parentheses x squared minus x minus 5. And let's zoom out a bit. Okay, so we found some critical points. Let's see if they check. We had a critical point at -3. So let me go in a little bit here. Whoops. So yes, it looks like right there is a horizontal tangent line. I could zoom in a bit more right here, and that is at -3. There's a horizontal tangent line right there. And then we found another one at x equals +2, and that's this little one down here. And if I was to zoom in, that is at +2. Oops, I keep going the wrong way. Right here, as you zoom in closer, it actually is more curved, and there is right there a horizontal tangent line is a CP, and that's when x is 2. Then the next question was at x equals 1, what happens? So let's go over here to x equals 1. Right here, x is 1. We intersect the graph right there. And we found that we should have a steep negative slope there. It is negative, right? The tangent line, if you draw it, would be decreasing. The function is decreasing there, and the tangent line has a steep negative slope. Yeah, and again, it is decreasing. Okay, so questions on that one? All right, I'm going to add one more piece to this then. How about we also do this? Because then we get to review some more things as well. Find the equation of the tangent line at x equals 1. Well, we know that tangent line has a negative lean to it, but we also know we went and found f prime of 1, we said was -4 times e. So we actually know to give a line, the line tells you it must be y equals mx plus b, right? That's the equation of a linear function. We know the slope m has to be f prime of 1, so we actually know that this goes right here. That's your m. And then to get the equation of a line, I just need to know this b. That's the last piece of the puzzle. So like at this point, we're here. We know that y is -4 times e times x plus b. And for the folks that -4e maybe is confusing, I'm just going to give you the decimal for that as well. (10.87). So this is -10.87x plus b. Right? To get the b, that's the last piece of the puzzle. That's the y-intercept for our line. We know it is a steep negative line, but the y-intercept, the best way to get that is if I just had an x and a y, then I could solve for b. I'd have one equation, one unknown. So do I know an x that I'm interested in? Yes, I know I want this tangent line when x is 1. That is our point of tangency. So I'm going to go ahead and plug that in right here. Y is -10.87 times 1 plus b. But when x is 1, what is y? Because I want to be able to fill in this part right here. Y, you go back to your original function. Y is a function of x, right? So if you give me an x equals 1, the point of tangency, I plug it in, I get e to the 1, 1 minus 1 minus 5. So maybe make a little space here. Y of f of 1 is e to the 1 times 1 minus 1 minus 5. So that is, those go away, minus 5 times E. So let's get the decimal for that. Again, folks that don't like seeing all those letters in there. 13.59. Right, so now I'm finally down to the place where I actually have one equation, one unknown for B. I can solve this equation for B, bring 10.87 to the other side, or get rid of the negative 10.87 by applying the inverse operation of addition. Whatever I do to one side, I do to the other. So I'm at this place. B is equal to whatever that is. Let's have calculator help us on that.
Wait, so where did you get the negative 13.59?
That is what negative 5 times E is as a decimal.
Okay, thank you.
Thank you. Oh, just 2.718. So if we do this subtraction here, we get B is negative 2.718. So our equation for the tangent line becomes y equals negative 10.87x minus 2.718. But we should also visually check that, right? So that is the equation of the tangent line. We had this graph that was basically something like this. Right, on Desmos, and we went to like -1 was right here. We had this, we want to get that tangent line there. So I want to graph the tangent line in Desmos as well, just to show us that we're doing, it looks like what it should look like, basically. So share the screen again, we'll go back to Desmos, and we'll add a function. That's our original function in red. Let's add the linear function, negative 10.87 x, negative 2.718. Whoops, need equal sign. And then in blue is the tangent line, and that's the tangent line at x equals 1. The tangent line changes depending on where you are in the function. And so when we zoom in, they should just barely touch, or the Latin caressed, kissing, they should just be barely kiss each other right there at 1, which is right here. The blue and the red coincide, they just barely touch each other. Oh wait, here's x equals 1. As you drag the point, x equals 1, right about there. Oh, pretty close, so right there. And that's when the blue and the red are just barely touching. Zoom out again. And again, that would be the direction of motion, where you just sail off if you're riding on a roller coaster in the forward or the backward direction, and you'd sail off in the direction of the blue line. Okay, so other questions on this one? Okay, so this one, just to review to make sure we've answered at least a few of the questions here. We got to do a product rule. We remember the function for that. We got to review what increasing and decreasing mean. We got to review equation of a tangent line and finding CPs. We also got to do e to the power rule. But there are also some questions about ln rules. So I want to do one more of those, and then we'll go to Taylor's question. She had a particular problem on page 150, and Elisa's got it. So there's a couple we could go through that are specific. Okay, so let's do an ln problem, and let's see if that's one of the ones that are covered by your questions here, guys. So you want me to look at page 157. Yes, okay, so I'm gonna take the first question from Taylor here. So she asked us to look at page 157. This is number 3 I'm picking to do. We want to differentiate okay, we want to differentiate this function, which just means take the derivative. They didn't ask us any other extension questions. They just want us to get good at taking the derivative. And the first thing we notice, okay, Taylor, I'll do that one next. The first thing we notice about this function is that it's got this ln, and then within that ln we have e's. So we're going to actually get to practice both types of rules, ln and e. The first thing is the ln. We need to handle that first. ln is a operation that does something to numbers. E is an operation that does the opposite. So if you take e of a number, so if you just take, like we're playing around on your calculator, put 2 in your calculator and then take e to the 2, you exponentiate it. It takes 2 and makes it bigger. It turns it into like 7-ish or something like that. But then if you were to take 2, put that in your calculator, and ln it, you do ln of 2, it squashes that number down and makes it smaller. So ln of 2, I don't know, maybe it's around 0.6 or something. So it pushes it down, whereas e's make it bigger. Those 2 operations are inverse. One's like expanding, one's compressing things. And the first thing on this, the ln operates first. And so we're going to do that ln rule first for differentiation. So the differentiation rule that we need, I'll put it over here. If your function is of the form ln of some stuff, doesn't matter what's in there. Our stuff is e to the x minus e to the minus x. Then the derivative y prime or dy dx or f prime of x, they all mean the same thing, is the derivative of the stuff over the stuff. All right, so that's the rule we're going to apply here, but for our particular thing, the stuff, again, is e to the x minus e to the minus x. So we copy that in the denominator, and then we put its derivative in the numerator. So here's where we get to use the next rule. If your function is e raised to some power, then the derivative is the derivative of the power times e to the power. We're going to get to use that twice because we have an e to the power minus another e to the power. So we're going to have something minus something. Okay, the first one, the derivative of e to the x is e to the x. That's either something you memorize or you just use this rule here. So it is e raised to the power. The power is just x. So I copy that, e to the x. And then I multiply it by the derivative of the power. The power is x. What's the derivative of x? That's just 1. It's the linear rule. So there's like an invisible 1 or an actual 1 there, however you want to think about it. And then the second function, e to the minus x, that's still an e to the power rule. So I rewrite it, e to the minus x. And then I multiply by the derivative of that power. So what is the derivative of minus x? That's minus 1, or just a minus sign. And if you want to clean it up a little bit, this will be e to the x plus e to the minus x divided by e to the x minus e to the minus x. Okay, on this page, it just said, differentiate that. Okay, so we give you back an answer. This is your final answer, and you're done with that problem. E to the x plus e to the minus x, all divided by e to the x minus e to the minus x. But again, like, what's the point? Who cares? Why am I differentiating? The reason you want to differentiate, think about your challenge problems. This will help you find whether you're increasing or decreasing. This will help you find where critical points are. This will help you find direction of motion. This will help you find the equation of the tangent line there, which again tells you where you would sail off. So I think there's a vandal problem for one of your challenge problems where there's a road and a car's traveling along a road and it has a paintball gun on the top of it. It's a vandalism problem and it's pointing in the direction of travel. So roof mounted paintball gun and traveling along this road, shooting off its paintballs. Well, they would go in the direction of the tangent line. That tangent line, you can get information about that tangent line from this derivative. So that's why we're taking these, doing this calculation here. It has a point, and you'll get to that point with the challenge problems. You'll get to that point in chapter 4, actually, as well. We'll have many applications for this, but we just want to get good at taking derivatives now. Okay, so that was number 3, and then Taylor wants us to take a look at number 5. Same page, number 5, different function, different instructions. Find the CPs for this function, y equals ln ax squared plus bx plus c. All right, well, this is the first time we've had one of these functions where it's a function of x, but there's all these letters over here too. So it's important to remember that the variable, it's a function of x. That's your variable. So that means a, b, and c are just constants. They're what are called parameters. I could change them for whatever problem I want. I might say a is 9, b is 5, c is 2. Solve the problem. I might say a is not 9, now it's 8. C is 5, b is 5, c is 2. So I might just slightly tweak things by changing the a, b, or c. And rather than doing that for like infinitely many values of a, b, and c, I can ask you a very general problem with these parameters. But don't worry, it doesn't actually make the problem any more difficult. So I'll show you why. If you want to take the derivative of this with respect to x, it's still an ln problem. So we're still using this rule. The stuff in this case is the parameterized thing, but the parameter is a quadratic expression. No problem. Just has some a's, b's, and c's that may eventually tell you which ones they're interested in. For now, we're going to give them a very general answer that works for any a, b, or c. Okay, then you look at that and you take its derivative and put that in the numerator. So what is the derivative of ax squared with respect to x? Well, again, x is your variable. A is just a constant. Just like put your favorite number in temporarily. Suppose it's 7. What's the derivative of 7x squared? 7 times 2 times x. But instead of 7, we had a. So it's going to be 2 times a times x. Right, so you're still doing times the power down a power. You're just leaving that constant as a parameter a. What's the derivative of b times x? Again, if it was 7x, what's the derivative of 7x? 7. So it's just going to be plus b plus 0. That's the derivative. You would stop if the instructions were differentiate this, but the instructions go a little step further. They say find the CPs. So the CPs for this are found by taking the function and setting it to 0. That looks a little intimidating because it's a fraction equal to 0, but remember the pretest and module 0. The only time a fraction is 0 is when its numerator is 0. So now I just need to solve this equation. 2ax plus b equals 0. I'm trying to solve for x. That is the variable, the only variable. There's a lot of letters in there, but x is the one that is the variable. These other ones are parameters that are actually represent constants that someone might eventually tell you, hey, I'm actually interested when a is 7, b is 5, c is 2. Okay, but now they didn't, so we'll just give them a general answer. 2ax equals minus b. Again, I'm either moving the b to the other side or applying the inverse operation of adding b by subtracting b. Whatever I do to one side, I do the other. Now I need to get at this x. It's right now is attached with this 2a. So how do I undo a multiplication? You do it by division. Whatever you do to one side of an equation, you have to do the other to be fair. So x is negative b over 2 times a. So I've now told them no matter what their function a, b, and c they give me, I could tell you exactly what the CP is. So great question, Taylor, thank you. All right, I think I'll maybe just do one more and then it's time to get on to this week's material. Okay, we already did a couple product rules. Let's do. Let's do one more product rule then. We'll do page 165. Okay, find the instantaneous rate of change of this function at 0. So what that's really asking you visually is to find the slope of the tangent line at x equals 0. So you could visually, graph the function, zoom into 0, and just sort of estimate what you think that instantaneous rate of change is. So let's quickly do that just to get a visual. This is good practice for your homeworks and quizzes and tests. So back to Desmos. Change the function. We're going to do e to the x minus x. We'll add some parentheses and change this function. X squared minus 4x. Oh, pretty similar. Minus 5. Okay. Zoom out a bit. One of these crazy, steep ones, huh? So, but we were interested in 0. I can zoom into 0. Right here when x is 0, so that would be our tangent line would look something like that. And so we know we should have a negative value because the instantaneous rate of change is just the slope of that tangent line, and we know we should get something negative. So that'll help us. We don't need to know exactly what it is, but it looks maybe steep negative, negative bigger than 1. Okay. So really another way of saying this is they could have just said find f prime of 0 for this function, right? That means the exact same thing. The way it's written, it's clear to see that this is a product rule. We have a first function and a second function. So we want to take the derivative and then we want to plug in 0. That's our steps. To take the derivative, we're going to need this structure. First function times derivative of the second plus the second function times derivative of the first. That's the product rule. Should I set that to 0? No, because we're not trying to find CPs. I don't take this equation and set it to 0. I take that equation and plug in 0, right? Two different things. Okay, so copying boxes. The first function is e to the x minus x. The second function is the quadratic, x squared minus 4x minus 5. And then I fill in the derivative boxes. The derivative of the second function is 2x minus 4. The derivative of the first function is e to the x minus 1. I'm really glad I don't have to set that equation to 0 because that would take a good bit of algebra to solve it for the CPs. I prefer, it's much easier. I don't have to simplify it all. I just have to look at this thing and plug in 0. Whenever I see an x, I'm going to stick a 0. So this is going to be e to the 0 minus 0. 2 times 0 is 0, minus 4, right? Plus 0 minus 0 minus 5. And then times e to the 0 minus 1. Anything to the 0 power is 1, or get out your calculator, type in e to the 0 or 0 and exponentiate it. So this is going to be 1 right here. So that'll be 1 minus 0 is 1 times minus 4 plus minus 5 times e to the 0 is 1 minus 1. So that's a big 0. That whole back goes away. So this is minus 4. We found the instantaneous rate of change at 0 was minus 4. And again, that's what we thought from Desmos. I think we're still on that page, yeah. So we said definitely negative, steep bigger than 1. That looks about right. If we wanted to actually make this a much longer problem, we could get the exact equation of that tangent line, enter it over here, graph it, and we'd see it would just barely touch there. Okay, so that's as much as we have time to review. I would suggest you up on these, talking to your teammates, talking to Chloe, reviewing the office hour videos that I did on Monday, and just reviewing the same videos that you already watched. It helps sometimes to pause them, rewind, watch again. Okay, yes? Okay, well, if no more questions, then it's time for us to jump in. This gives us an hour and 10 minutes to do chapter 3, get as far as we can on that. Chapter 3 is a much shorter chapter, but it has some interesting ideas in here. So we'll start right there on page 221, the very first page of the chapter. Okay, the first idea is just that you can take the derivative of a derivative. And so for the function, this example function on that page, f of x is x to the 5th minus x squared. Nice polynomial function. Easy to take the derivative. We already know how to do that from a couple weeks ago. 5x to the 4th minus 2x. We know all sorts of things we can do with that derivative, but here's what's new, is you could take the derivative of that, which is denoted f double prime. It's a second derivative, and it's just a couple more power rules, times the power down a power and a linear rule. You keep on going, you take the derivative of that. That's the third derivative, 1, 2, 3 little ticks. 60x squared minus 0. Continue on, take fourth derivatives, fifth derivatives, and so on. We mostly just focus on these top 3. We like the original function, which tells us a height on a graph, right? That's what f of x does. We like the first derivative, which tells us a steepness at some point on the graph. And then the second derivative, this is the next one we're going to use, and it actually is going to tell us something about how like bendy or curvy you are at a different point. It doesn't bend backwards very well, but like how curvy you are at a particular point. You could take higher ones. If you're a STEM major or physics major, you might see what these are useful for. At the bottom of the page there, you should read every page in the chapter, and anytime you see that gray font, do what it says, so it tells you to complete the table. The idea is that if your original function, so we're on this table here, if your function is y represents miles, x is hours, when you take a derivative, you're getting miles per hour. We talked about that with the road trip story. So when you take a derivative of miles per hour, you're doing miles per hour, which is miles per hour squared, which is a unit of acceleration. Often you see like meters per second squared. Again, those sorts of units are acceleration. If you continue, you'd be like miles per hour, which is miles per hour cubed, which is a unit of something called jerk. I think that word actually makes sense because if you learned how to drive stick shift, like it was really, jerky, you're actually quickly changing acceleration, changing velocity, changing acceleration makes a jerk. Okay, we're going to use these second derivatives. Again, the main thing is on the next page, page 222. To learn some words about concave up and concave down. And I want you to work through these pages on your own. You want to read these and fill in, circle the, when it tells you to circle something or draw a shape or fill in a little checkbox. You want to do those as you're part of your homework, as you're reading. And I'm going to kind of get us right to a punchline. A function, so that's in the box there. A function is said to be concave up if its derivative is positive. And then you're going to work out what that looks like on the shape of the graph at the bottom. And again, I'm going to get you to the punchline though. So a function is concave up. Often we abbreviate that like C up, which looks like the word cup, right? And it's when the function looks like a cup. Another way we often say it looks like a smile or part of a smile. So like this would work too. It's concave up there. It's concave up there. The reason those are concave up is because the rate of change of the derivative, so here's all of our tangent lines. Well, maybe I'll make it bigger. I stop and draw a tangent line. I stop and draw a tangent line. A tangent line is like zooming in on that function, or it's like sailing off on the roller coaster in either direction. When I draw those tangent lines, what's happening over here, they start steep negative, like say -10, and then like -5, -2, -1, 0, +1, +2, +5, +10, right? So they're actually, those rates of change are increasing. When your rate of change is increasing, your function's actually concave up. So that happens anytime you have something that looks like a cup or a part of a smile. They're concave up. Your rate of change, which is your derivative, is actually increasing. So again, on this example, if I just looked at this half of it, you are concave up because you're actually getting, your rate of change is increasing. It's getting steeper in this case. On the other hand, you're concave down if you look like part of a frown. So again, that's easy to remember because it rhymes. So that would be this, this, or this. Any part of a frown makes you concave down. In that case, your rate of change is actually slowing down. So like if I start here, I have a pretty steep rate of change. I'm increasing steeply, and then I sort of level off so it slows down. Your rate of change, not the function, but the rate of change. The derivative is slowing down. Okay, so you're going to read the next page, page 224, and that has a nice summary of the different shapes that you could see. All right, so you're going to go through that on your own. We'll go to the next page, page 225. And this just has a couple summary points, which is that if you have a linear function, your rate of change doesn't change at all, right? You always have the same, anywhere you stop and draw a tangent line, the derivative is the function. So your rate of change isn't changing, it's constant. That's okay, that can happen. And now let's get to maybe sort of the visual punchline for us. Page 226. Okay, so let's do this together. This is an activity, and so you're knocking out one of your pages for your homework from this section. All right, got a little more light. I just won't write over there because that reflection, it's hard to not have any reflection in this room. Okay, so I'm going to try to draw graph 2 on the board, and you can work graph 1 at home yourself, but I'm going to draw graph 2, a copy of it. You already have it on your page there. All right, so this is y as a function of x. They didn't give us an explicit formula, so we can't take, we can't use product rules, power rules, all that stuff to take a derivative because there is no f of x function. But we can still answer lots of questions and explore it. And the first thing is going to be, when is this thing increasing? So you should be good at that. Shade the graph where it's increasing. So this is the top half of page 226 for graph 2. You just want to shade along it where you're pedaling uphill, basically. Okay, so you have something like this. This is really easy. This is already review for us. Maybe I'll put it in the red. All right, so I'm pedaling uphill in the red, and then the question, one of the questions says, well, if you didn't shade it there, does that mean you're decreasing? In this case, whatever's not red, the black part, yeah, I'm decreasing. Yeah, I'm decreasing. Yeah, I'm decreasing. And they say, does that happen for every function? Or can you draw the function where there's a section or a point where it's neither increasing nor decreasing? So give that a shot. Can you draw a function where part of it or at a couple points, it's neither increasing nor decreasing? All right, anybody want to share theirs? You can always just hold it up to the screen.
Wouldn't a horizontal line not increase or decrease?
Awesome. Who's talking to me?
Lauren.
Lauren, thanks, Lauren. Lauren's right. So in fact, any section, so I could draw a graph maybe like this, a little one over here in the corner, really wavy, but then there's a section where it's horizontal. Maybe there's another steep, something like that. Any place where it is horizontal, it's neither increasing or decreasing. So Lauren's right. It doesn't have to be just because you're one or the other. You can actually be flat and have no increase or decrease. Okay, but most of the functions we deal with are these nice smooth ones. They don't have those because those are harder. We'll have like jagged points, which are non-differentiable. So we often see things that are more like this first graph 2 that we had up there. Now, I'm going to erase my red. And the bottom half of the page now, for graph 2, it says shade where it is concave up. So when it's concave up, you're just looking for any part of this graph that is like a cup or like a smile or part of a smile. So go ahead and go back through this function in the bottom half of page 226 and shade where it is concave up. You do that, I'll do that, we'll compare in a moment. I already broke my rule I wrote over there in the bright spot. Okay, so now I'm looking at this with a different set of eyes. These are now my concavity, like put on your concavity goggles, turn them on, boom. So it's concave up where it looks like part of a smile. So I think that looks like here until about here. And then it looks like part of a frown. And then maybe about here till about here. Starts frowning, maybe smiling from here to here. Frowning and then smiling. So it's concave up where I put the squiggles. And then this one asks any other part that you didn't shade, so just these parts, it's concave down. Yes, it is for this particular example. Do you think that's true for every example? Or can you think of a function where a section of it or a set of points is neither concave up nor concave down? So it's neither part of a smile or a frown. What might that look like? And Lauren's actually giving you a hint when she answered the question before about increasing or decreasing. What would it look like? What would a function or part of a function where it's neither concave up or concave down, what does it have to look like?
Would it be flat?
Nice. So who's just answered there?
Max.
Max, thanks, Max. So Max is saying it's flat, so that's a great example. So we could just have a function that's doing anything and then it gets flat, curvy again. Or also you could relate it to Max's answer, maybe it just gets like a straight line there. It doesn't necessarily have to be flat. So anywhere where you're linear means you're not curvy, right? If you're linear, you're not nonlinear, you're not curvy. So any section of a graph where we turn linear, we don't have a concave up or concave downness to us, we have no concavity. Okay, so this is kind of the picture for the whole chapter. What we're trying to do is figure out where on a graph, and again, we usually don't have these counter examples that Max and Lauren gave us. We usually have something that's this nice, smooth, continuous, bendy curve because we're doing polynomials for the most part in business calculus. And so we're trying to say where on this function are we concave up and where are we concave down? Again, we usually don't have places where we're neither, but it could happen. So where we're concave up or concave down is also going to tell us something about how curvy you are. That's towards the end of the chapter, this idea of curvature, which is a quantifying how curvy you are. So for now, we're just going to say one or the other, concave up or concave down, but we could say like you're really concave up there. Okay, so that's activity on page 226. You have a couple more pages of activities that are going to help you visualize these ideas. All right, and now we're going to go to page 233, possible inflection points. Okay, the first box I actually want to look at is the one in the middle of the page, the second box. This one here. We're going to learn a new term, the boldface term or the call out term, inflection point. You are an inflection point if the second derivative is 0 and your concavity changes. Okay, so that's going to be our key thing for us. And then we're going to find these actual inflection points by first finding something that's easier, which is the box above, possible inflection points. So and first maybe I'll just show you visually what they are. Actually, no, maybe we won't do that. We'll go to an example and then we'll come back to a visual. So now I want to go to page 235 and we'll start a problem. I'm going to modify it a little bit. This is number 1. The function is 1/3 x cubed minus x. And the first thing I want us to do on this one is find the PIPs. Okay, you just learned this term. So possible inflection point is a place where the second derivative is 0. Okay, so kind of like an extension of a critical point. Some folks call them hypercritical points, but most folks call them PIPs, possible inflection points. So we need to get our second derivative. The only way to get the second derivative is through the first derivative. And then we'll set that second derivative to 0. Nice polynomials. The first derivative is times the power downward power, so 1/3 times 3 is 1, downward power x squared minus 1. Second derivative is the derivative of the first derivative. Okay, so that's just 2x minus 0. I take the second derivative and set it to 0. I didn't have this big of an equation. It's a pretty easy one for us here. Starting out from baby steps. So we solve this and we say x equals 0. Is that a CP or a PIP or both? All right, again, we took the second derivative, set it to 0. By definition, that is a PIP. There was no need to stop back here at the first derivative and set it to 0. That would have given us x equals 1 and x equals minus 1. But those are CPs. We don't need those. That's like doing extra work. We just wanted to find the PIPs. Why do we want to find PIPs? Because those are possible inflection points, and really we want to find the actual inflection points. Sorry, I'm not supposed to write over there. You need to put a little box around this. This is my, can't write from here to, all right. So we also want to find the IPs, the actual inflection points. How do we do that? Well, back to the box, the definition of an actual IP is it's a PIP, okay? X equals 0 was our PIP. It's a PIP where the concavity actually changes from concave up to concave down, or vice versa. We just need a change in concavity. So what we're going to do to answer this, to find inflection points, is to take our PIPs this time. We had a PIP at 0. However many you have, you put them on an F double prime line. So this should start sounding really familiar. That's because it is. It's just like an extension of the F prime line. We only had one PIP, so again, easy starting problem. That divides us into 2 intervals. You pick a point from each interval, plug it into the second derivative. So F double prime, let's say, of -1, and maybe F double prime of +1. All right, we're going to plug those 2 things into the derivative, and we're really just interested in our signs. The second derivative at -1, oh, I erased my second derivative. I think that was F double prime of x was 2x, I believe. Yeah. Okay, so when I plug -1 into the second derivative, I get -2, but I'm really just interested that that's a negative sign. That negative sign was for the second derivative. So that tells you that it's concave down. Not that it's decreasing, right? If it was the first derivative and you got a negative sign, it would be decreasing. But we did into the F double prime. So that means we're concave down. We take F double prime of 1, plug it into the second derivative. F double prime of 1 is 2 times 1 is 2, which is positive. That tells you that you're concave up. When your second derivative is positive, you're concave up. When your second derivative is negative, you're concave down. Okay, so we took our PIP. We actually see that we do change concavity. We change from concave down, so part of a frown, and then we switch to concave up, part of a smile. Therefore, this can get an upgrade. This is actually an IP. It's a possible inflection point that turned out to be an actual inflection point. That's all the calculus, but like, what actually is an inflection point? So let's look at the graph and we'll see what an inflection point does and why it's useful for us. So let's put in our function, which was, let's see, 0.3333x cubed, right, 1/3 minus x. And so we have this cubic function. I keep doing the wrong way. Okay, we said that there was an inflection point at 0 right here. So we went from concave down, part of a frown, right until we get to 0, and then we switch to part of a smile. And that's what the F double prime line showed us. From -infinity up to -1, I'm sorry, from -infinity up to 0, so I'll just write it down and we'll come out of the screen share. We were concave down on the interval from -infinity to 0, and we were concave up on the interval from 0 to infinity. Again, we see that graphically. minus infinity all the way up to 0, we are concave down. We switch to concave up. So right at 0, because we changed concavity, by definition, you are an inflection point. It's an important point for us. Why is it important? So one of the main applications is, think about this red line. The function is a road that you're riding on. And let's say you're riding a motorcycle or a really fast e-bike, and you're riding along and you bend with the curve. And then right here at the inflection point, so you're leaning right. So again, just imagine your nose, you're kind of leaning to the right on your motorcycle, keep your balance through the curve. And then you're upright for a split second. And then you have to lean the other way to go along the curve this way. So that point where you change concavity is where you're exactly upright and balanced. You switch from a bend this way to a bend that way. These are really important for applications, like if you're, a great example is a luge track, or figuring out where it is super curvy. You might want to know it's super curvy here, so maybe I need to put guardrails maybe on this part, and that's the part we'll get to with the curvature. We can quantify how curvy you are. But right now, all we've done is figure out what an inflection point means. So it's visually a place where you're changing concavity, or thinking about it as a place where you lean from one side to the curve to the other and you're upright exactly at an inflection point. Okay. Okay, so we actually did, we did a problem on your homework on page 235 then. We did easy one, number 1. Let's do number 2 then. Let's do that one together. And we have now defined concavity, concave up and concave down. We know what it looks like visually. We know how to use that to find PIPs and IPs. And then we found concavity intervals with this F double prime line. So a lot of ideas, but they're really just extensions of things you already learned with the first derivative. We're now doing with the second derivative. All right, so let's practice number 2, because that gets us to practice ln rules. So actually, I wonder if we can do that one. Yeah, okay, let's do number 2. So same page, number 2, the function is now an ln. So we get a little more complicated here, but it's ln on a nice polynomial, so that's a good thing. We want to find, the instructions are find any inflection points if they exist. Some functions don't have any, like Max and Lauren already gave us a couple. Horizontal and linear functions don't have inflection points because they have no concavity. Okay, but to find the IPs, and then we want to ultimately find intervals of concave up and concave down. But they're really the same question. It's really saying, ultimately, you want to visually think of, in your little study guide over here, you're just doing an F double prime line, and you're putting any PIPs that you have on there, doing just like you would have done with an F prime line, but with a double prime. So you're going to plug into the second derivative, looking for sign changes. Those sign changes will tell you where your concave up and concave down. When you have sign changes, those PIPs get an upgrade to be called IPs. Okay, so that's the quick summary, visual summary, like for your study guide, or the algorithm of many of the ideas in this chapter. This particular function, though, then, if you're asking questions about concavity or inflection points, those both have to do with the second derivative. The only way to get the second derivative is through the first derivative. So let's do that here. Okay, welcome, DeMarco. Okay, f prime of x, the first derivative, is an ln rule. So do we still have it? Yeah, derivative of the stuff over the stuff. So the stuff is 4 plus x, the derivative is 2x. I don't need to do anything. I don't need to set that to 0. I don't need to plug in any numbers there, because that's the first derivative. It's asking us questions actually about the second derivative because they're IPs and concavity. So I need to just use that to get to the second derivative. The only way to do that is through the first derivative. Cool. Glad to hear that, DeMarco. You're back in. Wi-Fi is weird sometimes. Okay, so this one though, I told you we don't have to use we didn't have to learn the quotient rule, that we were just going to use the product rule. So here's an example where I'll show you how to do that. So this function looks like it would need a quotient rule because it looks like a quotient, but using properties from the pretest and module 0, right, this is really all raised to an invisible 1 power. It crosses the bar and goes up to the -1 power. Once I've written it like that, it's now a first function times a second function. Now we get to do a product rule in order to take this derivative. Okay, so we put our structure, first times derivative of the second plus the second times derivative of the first. Okay, some copy boxes. Some derivative boxes. Okay, then the last derivative box is the general power rule, and I don't think we've gotten to do that together in class, so I'm going to add that over here to our differentiation rules. Okay, this one's called the general power rule because it kind of looks like the power rule. It's just a generalization of it. So if you have some function raised to the n, not just x, the power rule is just for x, but you have something more complicated than x raised to a power. What we do, we have 4 plus x squared. That's like the f of x part. It's something raised to a power. If that's the case, so that is our second function. It fits that form. So we're going to need the general power rule for differentiation. Then you go times the power, take that thing in parentheses down a power, times the derivative of what's inside. So that's a good phrase to remember again. Times the power, take that thing down a power, times the derivative of what's inside. Okay, so we're going to do that. This is our first general power rule as a group here. Times the power, -1, take that thing in parentheses down a power, times the derivative of what's inside. So again, that's our first one, so I'll let it sink in for a bit. We used what's called the general power rule. If you have some function of x, not just x anymore, something a little more complicated, like we did, 4 plus x squared was raised to the -1. So you go times the power, that's the -1. Take that thing in parentheses down a power, I subtracted 1, times the derivative of what's inside the parentheses. So that was 4 plus x squared, its derivative is just 2x.
So does the ln just go away?
Yes, with the ln rule, your function has an ln, but the derivative doesn't. That's a great question, and it's kind of complicated for students to think about that too, because again, ln is an operation. What happened to it? Why does it go away? It's because mathematicians have figured out we can avoid the limit definition of the derivative and take the derivative and just get this.
Okay, thank you.
Thank you. All right, but what are we doing with this? Like, this is a long, messy looking thing, but what is our goal at this point? So just think about that. Like we did heads down, writing on paper, writing on a whiteboard, lots of calculating, but like, what's the purpose at this point? So go back to the problem. What are we trying to do? We're trying to find inflection points. Where do inflection points happen? They happen at possible inflection points. What are those? Those are places where the second derivative is 0. So I have to take this second derivative now and set it to 0. So I have a big equation like this. Right? That looks pretty messy, right? We've got this long thing, we've got some exponents, but let's just take a moment and we'll see it's not as bad as you think. So let me do a little algebra. You guys just watch, spectate. I'll do some algebra. Okay, so I have a 2x times a 2x. That's a 4x squared. Then I'm going to take this thing raised to the power and put it in the denominator. So it'll actually come back and be 4 plus x squared, all squared. Crosses the bar again, becomes a positive then. And I still have my minus sign. Maybe I'll just put that up top. So that's the first term. It actually just simplifies to this. Maybe that's nicer to look at. We'll see in the next step. Plus the second term is just going to be a 2 in the numerator and then a 4 plus x squared in the denominator. A little bit cleaner to look at, but I still have this to set that thing to 0. So I still have to solve this equation. This equation is a fractional equation. So one step is to maybe take, I have 2 fractions here. Maybe I could turn them into 1 fraction.
Can you?
So that's what we're hoping we can do with some algebra. And I see that there's almost a common denominator. Like if I just multiply this one by another 4 plus x squared, I'll have a common denominator. But I can't just multiply the denominator by 4 plus x squared unless I do the same thing to the numerator. I have to be fair to that fraction, right? So really what I'm going to have is minus 4 over x squared. I'm going to leave this first fraction exactly the same. And then I'm going to multiply the second fraction by a special 1, which is 4 plus x squared times 4 plus x squared.
Will you go back for 1 second and
Yes.
repeat how you got that step right before, like when you moved it to the, yes, that, will you just say that part one more time?
Yes. What's your name?
Macy?
Macy, thank you. Okay, Macy wants to know from here to here, I think is
Yes.
the idea. Okay, so I saw a 2x times a 2x and I made that 4x squared. I saw the minus sign and I just left it there. And then really the only trick to this one was this part here. That is 4 plus x squared to the minus 2. Well, if it crosses a bar, it becomes 4 plus x squared to the minus 2. So all I did was like flip that back into a fraction. And I did the same thing with this second term. I left the 2, and then this is 4 plus x squared to the minus 1 is the same thing as 1 over 4 plus x squared. So I just put it like that.
How did you get the -4 again?
Say that again.
How did you get like the -4? I get why it's 4, but I'm kind of confused why it's negative.
The negative sign came from that right there.
Oh, okay. Thank
Yeah,
you.
There's a little one hidden.
And how did you get from 2 to 2 with the 4 plus x squared for the second step?
This line down here?
Yeah. Mhm.
Okay, good. Okay, so I feel like we're okay here. And now I'm just getting to practice algebra. So this is not the calculus, right? We're just algebra massaging this guy. And so we get to review things that you probably haven't done in a while. So just showing you a few tricks here again that we can like move that one down. And now the next question is, how did I go from this line to this line? Or what I'm doing is I'm trying to turn these 2 fractions into 1 fraction. If I just had 1 fraction, then there's this nice rule that you just set the numerator to 0, and so we're almost there. I'm just trying to turn it into 1 fraction right now. I have 2 fractions at this line. I'm hoping I can get a common denominator, and then I'll turn it into 1 fraction. So to get the common denominator, I'm almost there because I see that they both have this 4 plus x squared. This one just needs another 4 plus x squared. So I left the first fraction the same. And the second fraction, I just multiplied both the numerator and denominator by 4 plus x squared. Because really that's, right, this part here is just a special, I haven't changed the fraction. That's just a special way of writing 1, right? Something over something is just 1. So I haven't changed the fraction. I guess my point is I'm allowed to do that. That's what I'm saying. I'm allowed to do that because I haven't changed the fraction. The purpose for doing that was so that now I have the same denominator for both of those. When you have the same denominator, you can combine the numerators, right? So really it's to this line. Right, so now I'm almost there. I've turned it into one fraction. Took the two fractions, got a common denominator, took those two fractions, added the numerators because they had the same denominator. I'm allowed to do this. And now maybe make some space. Right in here.
Wait, so can you repeat how you got the 4 plus x squared in the numerator?
This one here.
Yeah.
Yeah, again, so what I did, the fraction was just 2 over 4 plus x squared. So the original fraction, I don't know if you can see the colors very well, but it was just this. Maybe I'll get that red. Right, that's the original fraction in blue there. And then I multiplied it by this special one, this part here. The purpose of multiplying it by 4 plus x squared divided by 4 plus x squared was so that the denominator would be 4 plus x squared all squared. So it'd be the same.
Okay, thank you.
Okay, so we're in this last box over here. I want to just simplify this, and we're almost there. So that's negative 4x squared plus 8 plus 2x squared in the numerator. The denominator stays the same. So that is negative 2x squared plus 8 over 4 plus x squared all squared. All right, and that equals 0. That's the equation we're trying to solve, which is really just the second derivative equals 0. It just so happens I chose a difficult one here. When the second derivative is equal to 0, we are getting PIPs. So I want to solve the equation in the box here. This equation looks messy, but remember from the pretest, the only way a fraction can equal 0 is if the numerator equals 0. And so to really get it even simpler, I just have to solve that. Now I'm going to, if you guys are okay with it, I'm going to take away all this algebra, unless someone needs me to slow down. All right, I don't hear any objections. I'm going to start erasing. Okay, negative 2x squared plus 8 equals 0. This is something we can solve. It looked so messy before, couple pages on the whiteboard, whole notebook page for you guys, but we're down to something that is doable. So I'm going to remove the 2x squared to the other side. I'll leave the 8. I'm trying to solve for x. It's stuck with this 2 right now. I get rid of multiplying by 2 by the inverse operation, which is dividing by 2. So I have 4 equals x squared. X is stuck inside the squaring operation. To undo that, you do the inverse operation, which is square rooting, but whatever you do to one side, you do to the other. So I really have to also remember the plus minus. So I have plus or minus 2 is equal to x. So x equals 2. X equals minus 2. Those are PIPs, not CPs. PIPs because we took the second derivative and set that to 0. What made this problem so messy was the second derivative had that fraction in it. No, sorry, the first derivative had the fraction, and then we had to use the product rule, made more fractions. But we're finally to the place where we know that these 2 points are possible inflection points. We won't know if they're actual inflection points, like it asked us, until we do the F double prime line. But we're almost there. That's the easier part. F double prime line, just like an F prime line, but we're going to be plugging into the second derivative. Remember though, it's a number line, so you put your points, which are PIPs in this case, in number order. So that would be -2 first, then the 2. Those 2 points divide your number line into 1, 2, 3 intervals. You pick a point from each interval, you plug it into the second derivative, that's why it's important to label that line, and then you check, is this second derivative positive or negative? If it's positive, if the second derivative is positive, you know you're concave up. Second derivative is negative, you know you're concave down. If there is a sign change, you know the PIP is actually an IP. So let's not worry about this particular problem for a moment. Let's just pause and suppose we got an F double prime line that looked like this, plus, plus, minus. How would you interpret that? You would say that the function is concave up from -infinity all the way up to 2. Then it's concave down from x equals 2 all the way up to infinity. You would furthermore say the PIP at -2 is a PIP. It doesn't get the upgrade. On the other hand, the PIP at x equals 2 gets an upgrade because it changed sign from concave up to concave down. That's actually an IP. It's the place where you're riding your motorcycle, leaning one way, stand up for a second, leaning the other way. Didn't happen here. We thought it might, but it didn't. Okay, so that was just a general scenario, but let's go back to our specific problem and see if we are positive or negative on each interval. And so we need our second derivative to plug into, so let's just go back to, let me make some space here. Our second derivative, when we did all that simplifying, we got down to this was the second derivative. What's in the box, and we don't need the equation equals 0, it was just this fraction. That's our second derivative. So we need to plug in points to that fraction. We try something over here, like -3, F double prime of -3. So we're gonna have a fraction in the denominator. It's always positive. It doesn't matter what I plug in, I'm taking something and squaring it. So that's always positive. The numerator, when I plug in -3, will be 9 times -2. So -18 plus 8 is negative. A negative divided by a positive is negative. So this first interval from -infinity to -2 is concave down. Pick another point, maybe we try 0, F double prime of 0. It's a fraction. The denominator is always positive no matter what I plug in. The numerator will be 0 plus 8 is 8, which is positive. A fraction that is positive divided by positive is positive. So we know on the interval from -2 to 2, we are concave up. One more interval to check. Maybe we'll try the point +3 over here. F double prime of +3. Again, once again, it's a fraction. The denominator is always positive because I'm squaring something. The numerator in this case will be 9 times -2 is negative. 18 plus 8, -10, so that's a negative. Negative divided by positive is negative. Again, you would write it out to summarize. You are concave up on the interval from -infinity to concave down on the interval -infinity to -2, and from 2 to infinity. You're concave up on this small little section from -2 to 2. You're concave up, you look like a smile or part of a smile. And therefore, both of these PIPs turned out to be IPs. So we actually have an IP at x equals -2 and an IP at x equals 2. Well, that was a lot of calculus. I don't know, probably took us 15 minutes, right, to do that one problem. But let's check, after all that calculus stuff and lots of algebra, let's check what this looks like. So we'll go to our function, put the function into Desmos. So we're taking an ln of 4 plus x squared okay, we have this sort of symmetric shape here about the origin, and we said that we were concave down from minus infinity to minus 2. So maybe I'll zoom in a little bit so we can see the minus. Oh, why did I do that? To minus 2, which is right here. So we're saying that we're concave down, we're part of a frown, and then right there at minus 2, we switch and we're part of a smile. And that's true until 2. So just that little section right there, we are concave up, we are like a cup, we hold water, or we're part of a smile, and then we switch right there. And again, this is why you want to know this precise point at minus 2 or 2, is again where it changes exactly. It's not like, it's not over here, it's exactly right there where you change from the frown to the smile, because that's, again, riding a motorcycle, we're leaning into the curve, we're upright, and then we're leaning into the other curve, right? And so it's nice to be able to always visually check your work.
So the IPs of -2 and 2, where did those come from? Because I thought we were looking at -3 and 3.
Oh, who's asking the question?
Lauren.
Lauren, thank you. Great question. So Lauren's question, we had PIPs, which came from solving this equals 0, right? This equation that was in the box. We spent a lot of time and we got possible inflection points at -2 and 2. So Lauren's saying like, okay, well, they're there, but what are these 3s and -3s? Those were our test points, Lauren. So remember your F double prime divides, those PIPs divide the F double prime into 3 intervals. You pick a point, any point from each interval. It doesn't matter whether you pick -3, -4, -10, -100. You'll always get a minus sign on that interval. And that minus sign means you're concave down. So I just chose that -3. I chose 0 in the middle here. I chose 3. You could have chosen a lot of different points yourself. Again, you could have said maybe -5, 1, and 100. They would have worked.
So the 2 and the -2 come from setting the second derivative to 0.
Awesome, great summary. So a possible inflection point, in this case, the 2 and the -2, always happen. That's your definition. When the second derivative is 0, that's a PIP. And then you're going to check with the F double prime line, is each one of those PIPs an actual IP, by doing just like you did for the F prime line, but it's a double prime line. So again, a summary of like this versus F prime, you put CPs on this one, you put PIPs on the double prime. This tells you increasing or decreasing. This tells you concave up or concave down. This tells you, well, actually, I can't say that yet. We'll wait till you get to chapter 4 on that one. Okay, so that was page 235. We already did a couple of those, so you have some more due for your homework. And then there's a couple activity pages, page 238, 239, these Kirby sketch ones. Those are just making sure you know, again, your vocabulary and how to visualize concavity, because Lauren asked some really good questions. Students really have a hard time. We learn so much so fast in this class, but make sure you can distinguish between these two things. One's an F double prime, tells you certain information. That second derivative tells you information about concavity, concave up, concave down, and possible inflection points, inflection points. The first derivative tells you information about instantaneous rates of change, tangent lines, slopes of tangent lines, equations of tangent lines, increasing or decreasing critical points, right? So that's sort of the summary of all the information you get from the first derivative. And then the second derivative, you get different complementary information. Okay, we got a little more time today, so let's do a little more in chapter 3 together. The next set of activities, and this is part of your homework too, is the exhibit of curves. So what page is this? Page 240. And we're going to do a few of these together. Let's see. On page 241, Okay, there's a graph, and I'm gonna try to copy mine that looks similar to yours. Okay, and then what you're supposed to do on page 241 next to that graph number 2 is take a moment now and write as many things as you can. You have a pretty good vocabulary at this point to describe graphs. Like, can you find places where it's increasing? Can you find critical points? And there's a list on the previous page, page 240, of some things you could answer. Are there any critical points? Where are there? Are there inflection points? Are there possible inflection points? Does it have any intercepts on the X or Y axes? This one doesn't have axes. Is it linear or nonlinear? Are there any non-differentiable points? So just make the longest list you can to describe things about that graph there, graph 2. Okay, so let's see if we can do this together and make a list. Let's think about critical points. So critical points are places where you have a horizontal tangent line. Well, there's one right here, one right here, one right here. So you start labeling some stuff. Some other first derivative stuff is, how about where you're increasing? That's where you'd be pedaling uphill. So it looks like uphill, maybe, mine's a little wavy right there. I don't know if I copied it very well, but increasing there, then we're downhill coasting, uphill, and uphill. Increasing on those little squiggly sections. This one didn't have any axes, so I don't know where we can say x-intercepts or y-intercepts on this picture. But there's also one point that's non-differentiable, so think about that. It's been a while. But a point is non-differentiable if it doesn't have a derivative, and this might have been all the way back to chapter 1, so several weeks ago now. You are non-differentiable. For us, we talked about this nice analogy that it's a point where you're riding the roller coaster in the forward direction, and you get a certain tangent line, and then you ride it in the backwards direction, and your tangent line doesn't match. You have two different tangent lines. Every other place where you're smooth and continuous, those tangent lines will match, whether you're riding that Rebel Yell forward or the Rebel Yell roller coaster backward. So there's one point here on this graph that's non-differentiable, and it's this guy right there. So this point is non-differentiable. It means there's not a derivative there. If they had given us an explicit function, y is a function of x, we couldn't take a derivative there, again, because if I was riding backwards, I'd sail off like this. If I'm riding forwards, I'd sail off like that. Those two tangent lines don't match. Any other point you're at, like every one of those CPs, obviously, any other point on this function, the forward and backward tangent lines match. Okay, what else can we say? We now learned some stuff about the second derivative. So can we find inflection points? Those are places where you change concavity. So maybe we need to put some concavity information in there. So let's do concave up. I'm going to do that in red on mine. You're concave up where you're part of a smile. So it looks like here to about there. And then you're frowning. And then you're smiling for a little bit, frowning, Browning. So those are approximations for this visual graph. Again, if they gave us an explicit function, we can tell them precisely where you're concave up or concave down. Here we can just estimate. So the red parts, the red squigglies were concave up. You're concave down on the other sections. Yeah, and there's no places where Max or Lauren's idea where it's linear. So there's no places where you're neither concave up or concave down on this particular function. And then inflection points. So you are an inflection point if you actually change concavity. So let's see, we were concave up and then we switched to concave down. So this point right here is an actual inflection point. And we stay concave down and then we go concave up. But we're non-differentiable, so we won't be able to find those. And then we're concave down and concave up. So an IP right there. Okay, so this activity, you do that, fill it in, make the longest list you can of verbal descriptions of those different graphs. We just did graph 2, but there's 1, 3, 4, and 5. Flip the page 242, and graph 5, you actually fill in a graph. So you just sort of draw a smooth continuous function that represents your bank account over the last few years or something. Okay, then another set of activity pages is pages 244 and 245. These are your summaries of the information that the derivative and the second derivative give you. Remember in chapter 1, was it? The end of chapter 1, we had very similar pages, but they were f versus f prime. Now we're doing f prime versus f double prime. So we want to make sure we understand the difference of what the function, the derivative, and the second derivative give us. And so these are good summary pages. So go make sure you take your time and go through those carefully. Do it for your homework. Okay, the last set of pages is about curvature. Remember I told you that we can actually define how curvy you are at a point, and we can create this function, k of x, that tells us precisely how curvy we are at any point x on the graph. That's really cool because you can do things like this. This is a simple function, but you can find out where's the curviest place on this cubic function. So again, if this was a road and you wanted to put some guardrails, you could find out, okay, well, you probably should put them near, right before, right after those curviest places. If you're going in this direction, you want them right after the curviest point. And so we can quantify that precisely. And then there's a neat connection to curvature and something called osculating circles. However, really cool stuff, but this is optional for us when we teach business calculus. So these last few pages, if you want to read them and look at the pictures, that's useful, but we don't have to do the calculating. So pages, we'll put this over here, pages 248 through page 252. They're all about curvature. Again, you're welcome and you should just read and look at the pictures. Again, it's useful ideas. It's just something that for business calculus is optional. Okay, then the last couple pages of this chapter are algorithm pages. So these are pages 254 and 255. And so that word, I've used it a few times already this semester, is a big part of my research. I love this word. But it actually comes from the name of this Persian mathematician, Al-Khwarizmi. And algorithm just means a numerical recipe. And so some of you, when you've learned math in the past, or you really prefer to think about making your study guides for the final exam as like step 1, step 2, step 3. I think a couple folks put that in the challenge problems. So start doing this. Start making algorithms with different steps. It's just a set. It's almost like a cooking recipe, but it's for math. Step 1, you do this. Step 2, you do that. Step 3, you do this. There's many different ways to solve a particular problem. Like for instance, finding the critical points, here's 3 different algorithms in the 3 boxes to find those critical points. There's probably one that you prefer though. So write that down or write your own. And so on this next page, page 255, page 255, it's asking you some of the main calculation problems that we've done thus far. Chapters 1, 2, and 3 really boil down to just a few type of problems. Find the equation of a tangent line. Find the equation of the tangent line is the first box. So you could think about that as step 1, step 2, step 3, if you want to write it that way. Or maybe you think about, if you're a visual learner, is there a picture that draws that like jogs your memory of how you solve those? The other type of problem, find the instantaneous rate of change of y with respect to x over here in this box. Honestly, those are really almost the same question. Instantaneous rate of change is just asking you to find a slope of a tangent line. Maybe not the whole equation like here, but just the slope of the tangent line. Let's see, find intervals of increase and decrease over here. This was one where we could just do an F prime line. So again, if you're a picture person, maybe you put your F prime, CP1, CP2, CP3, put an example of looking for sign changes. Find intervals of concave up and concave down. That's just an F double prime with PIPs on there, PIP1, PIP2, and so on. So you could draw little pictures maybe that'll help you understand that, or an example function, work through one example, or again, if you like to think steps, write your steps here. And again, we didn't do this last box on curvature. So you don't need to find curvature or osculating circles. Okay, then there's some challenge problems as usual at the end of every chapter. Every chapter also, these are good things to start just casually going through and getting ready for your final. Always have study guides, just sort of your vocabulary. Maybe you give an example or a picture or something here and answering these questions. Some more keywords maybe, just filling in things that are key concepts from that chapter. And then they always have your concepts and calculation questions. You've seen plenty of these now in the quizzes. Many of the concept questions come from or related to what you see here. And they always have answers following. This is a good place to look. There's also, you will see problems very similar to this or exactly taken from the concepts and calculation reviews at the end of every chapter will make up your final exam. And so calculation reviews show the main types of problems that you did in each chapter. And there's really only in this case 5 different types of calculation problems, of which you don't even do the last one. So there's really 4 different types. So you just don't have to make too many of these algorithms when you're thinking about step-by-step things for each type of problem. Okay, so that's chapter 3. And then the last chapter is when we're really getting into chapter 4, why we're doing all these derivatives. You just spent chapter 2. That was really what I would consider one of the more painful parts of calculus. You're just cranking away calculating derivatives. Why you're doing that, we're now getting to chapter 4. There's some cool applications. Your challenge problems have some, but there's quite a bit in chapter 4 where, again, we're trying to minimize cost, maximize profit, optimize dimensions of a shed that we need to build. So there's nice applications finally coming next module, so next week. All right, so don't forget your challenge problem this week, do with your group. So meet up with your group and get started going through. I purposely did that too because chapter 3 is a little bit lighter and shorter. Then you can also focus on both things this week. Okay, so any questions? We have a few more minutes. Any questions for me? Otherwise, if you don't, you're free to sign off. Thanks for sticking around so long tonight.
Class.
Thank you.
Okay.
Thank you.
Yeah.